Welcome back, everyone, for another deep dive. This time we're going to be taking a really close look at the paper 1511.04508, Distillation as a Defense to Adversarial Perturbations Against Deep Neural Networks.
Oh, this is a good one.
Yeah, this is a really interesting paper, and I think, for our listeners, as experts in machine learning and data science and all that, you're very familiar with deep neural networks and how powerful they can be.
DNNs, for sure.
Yeah, but you're also probably aware of their vulnerability, to adversarial samples. And so that's really what this paper is all about, is a new defense mechanism. It's called defensive distillation.
Okay.
And I'm really excited to kind of unpack this with you. The results are pretty impressive. They're claiming to reduce, in some cases, the effectiveness of adversarial samples from like 95% to less than 0.5%.
Wow. That's a pretty big reduction. So this paper really dives into a very important aspect of DNN security, especially for, those of us working with these networks and in applications where these vulnerabilities could have a real-world impact.
Absolutely.
Yeah.
So let's kind of start with the basics, right? We all know deep neural networks. They're super powerful for classification tasks.
Yeah.
But because of their reliance on these like very complex nonlinear relationships, they're susceptible to these adversarial samples,
Right.
which are basically just these carefully crafted inputs that are designed to mislead the network.
Yeah. And they can be so subtle. Like, they're often indistinguishable from the real inputs to a human observer.
Totally.
But they can completely throw off the DNN
Right.
and cause it to make totally wrong predictions.
Yeah, and the paper talks about some examples, like, think about a self-driving car that misinterprets a road sign because there's like a tiny sticker on it that we wouldn't even notice.
Right.
Or, a malware detection system that fails to identify a threat because like a few bytes have been changed in the file.
Yeah, scary stuff.
The implications for security are pretty huge. So we really need to figure out these robust defense mechanisms. Okay, so let's talk about, like, how are these adversarial samples actually created?
Yeah. So the paper outlines like a two-step framework that attackers typically use.
Okay.
So first, they'll try to estimate the direction sensitivity of the DNN. And that involves, using techniques like the fast gradient sign method or the forward derivative to identify which features most influence the network's output.
Okay, so they're trying to figure out, like, the weak spots, essentially.
Exactly. Like, what are the things that the network is most sensitive to? And then once they've identified those, they'll go to step 2, which is strategically selecting these perturbations. And this might involve using, tools like saliency maps or just perturbing all the input dimensions to really exploit those sensitivities that they found in step 1.
Okay, so they're kind of like poking and prodding the network to see where it's most vulnerable.
Yeah, exactly. And then once they know where those vulnerabilities are, they can carefully craft those perturbations to basically force the DNN to make the wrong classification.
Got it. Okay, so the defense mechanism, it's called defensive distillation.
Right.
But before we can really understand that, we need to go back to like the concept of neural network distillation.
Okay.
Because defensive distillation is kind of an adaptation of that technique. So, originally, neural network distillation was developed to like transfer knowledge from a larger DNN to a smaller one as a way to reduce computational complexity without really sacrificing performance.
Okay.
So basically, you've got this big network, right? It's been trained on a huge amount of data,
Right.
and it's really good at what it does,
Right.
but it might be too computationally expensive to use in like real-time applications.
Makes sense.
So what you do is you use this larger network to generate what are called soft labels.
Mm-hmm.
These are essentially probability vectors that capture the likelihood of, a given input belonging to each class.
Yeah.
And then you take these soft labels and you use them to train a smaller network. And the smaller network, it basically learns from the larger networks, like more nuanced understanding of the data.
Ah, okay. So it's like the smaller network is sort of learning from the wisdom of the bigger network.
Exactly, yeah. It's
Yes.
like a mentorship program for neural networks.
I like that.
So how does this all translate to defending against these adversarial samples?
So that's where defensive distillation comes in.
Okay.
And it's basically a clever adaptation of this original distillation technique.
Okay.
So it involves 4 main steps. And the first step is you train the initial network, the big one, at a high temperature.
Okay, high temperature. What does that even mean in this context?
Yeah, so the temperature, it's a parameter that affects the softness of the probability distributions that are produced by the softmax layer.
Okay.
So a higher temperature basically leads to softer, less confident predictions.
Okay, so it's like it's making the network a little bit more uncertain about its outputs.
Yeah, exactly. It's preventing it from being too overconfident, you could say.
Okay, and why is that important?
Well, we'll get into that a bit more later, but basically it has to do with how this high temperature affects the network's sensitivity to those adversarial perturbations.
Okay, so step one, we train at a high temperature. What's step two?
Step 2, we generate the soft labels from this initial network.
Okay.
And then step 3, you train a second network. And the second network has the same architecture as the first one, but you train it using those soft labels that you generated in step 2.
Okay, so we're basically distilling the knowledge from the first network into the second network.
Exactly. And importantly, you still train the second network at the same high temperature.
Okay.
And then finally, step 4, you use this distilled network for prediction at test time, but you set the temperature back to 1.
Got it. Okay, so it's like we're training this network in a more relaxed environment with this high temperature, and then when it's time to actually make predictions in the real world, we kind of like sharpen its focus by setting the temperature back to normal.
That's a good way to think about it.
Okay. Now, the paper also mentions some key requirements for this defense mechanism to actually be effective.
Right.
Like, it needs to have minimal impact on the DNN's architecture, it needs to maintain accuracy and speed, and it needs to be effective against adversarial samples that are close to the training data.
Yeah, those are all important considerations. Basically, we want a defense that's practical to implement, doesn't slow down the network, and can actually protect against realistic adversarial attacks.
Right. It can't be this, like, super computationally expensive thing that only works in, like, very specific scenarios.
Exactly. It needs to be something that we can actually deploy in real-world application.
Makes sense. Okay, so how does defensive distillation actually change the network's behavior?
Right, so let's dig into that. The paper analyzes the impact of defensive distillation on two main things.
Okay.
One is network training, and the other is model sensitivity.
Okay, so how does it affect network training?
So during training, the use of those soft labels that we talked about, it leads to a different optimization problem compared to traditional training where you're using, those hard labels.
Right, so instead of just saying, like, this image is a cat, we're giving the network a probability distribution over all the possible classes.
Exactly. And that encourages the network to learn smoother decision boundaries.
Okay.
Instead of being forced to assign each input to a single class with 100% certainty, the network learns to distribute its belief across multiple classes.
Okay.
And that makes it less susceptible to those adversarial perturbations because it's not relying so heavily on specific features that an attacker could easily manipulate.
So it's kind of like it's making the network less brittle, less prone to breaking when you make those tiny adversarial changes to the input. Okay, that makes sense. And how about model sensitivity? How does defensive distillation affect that?
So remember that Jacobian matrix we talked about earlier?
Yeah, that captures how sensitive the network is to changes in its input.
Right, exactly. And what the paper shows is that increasing the softmax temperature during training with defensive distillation, it leads to a significant reduction in the absolute values of those Jacobian matrix components.
So it's making the network less sensitive to those small changes in the input.
Exactly. And because those adversarial attacks often rely on those tiny, subtle perturbations, this reduced sensitivity makes the network more robust to those attacks. It's like defensive distillation is smoothing out those decision boundaries, making it harder for attackers to find those really vulnerable points.
That's interesting. So by making the network less sensitive overall, we're essentially making it more resilient to those very specific targeted attacks that rely on those small changes.
Yeah, it's a really clever approach.
It is. Now, the paper also touches on how defensive distillation affects the DNN's ability to generalize beyond the training data, right?
Yeah, and this is a fascinating aspect.
Okay.
So they give this really interesting example using handwritten digit recognition.
Yep.
They argue that those soft labels, by encoding information about the structural similarities between different digits, they can actually improve the network's ability to recognize new examples that it's never seen before.
So it's not just about making the network more robust to attacks, but it's also potentially improving its overall ability to learn and generalize from the data.
Exactly. And they connect this to this idea of stability and learning theory, suggesting that defensive distillation, because it encourages those smoother decision boundaries, it leads to a more stable learning process, which in turn enhances generalization.
That's fascinating. So it's not just a security benefit, but also a potential improvement in the overall learning capabilities of the network.
Right, exactly. It's a really intriguing result.
Okay, so we've talked about the theory, how defensive distillation works, how it affects network training and sensitivity. Now let's move on to the evaluation phase. Let's see how these theoretical insights actually translate into real performance.
Yeah, let's see how it does in practice.
So the paper evaluates defensive distillation using two widely used datasets, MNEST and CFAR10.
Right, those are pretty standard benchmarks for, evaluating image classification algorithms.
Yeah, and they're often used in adversarial machine learning research as well. So it's a good choice for this kind of evaluation.
And what kind of DNN architectures did they use for these experiments? Because it's important to make sure that any improvement in robustness isn't coming at the expense of basic classification performance.
Yeah, absolutely. So for MNEST, they used a 9-layer convolutional neural network. And this architecture, it achieved a classification accuracy of 99.51%, which is pretty comparable to the state-of-the-art DNNs for this task.
Okay, so they're working with an architecture that's already very good at classifying handwritten digits.
Right.
What about CFAR10? For CFAR10, they also used a 9-layer convolutional neural network, and they achieved an accuracy of 80.95%, which is, again, in line with current top-performing models.
Okay, so they've got these two data sets, and they've got these DNN architectures that are already performing really well in their respective tasks. So this provides a good baseline to evaluate the impact of defensive distillation on robustness.
Exactly.
So how did they go about crafting those adversarial samples to test the effectiveness of their defense?
So for this, they used an adversarial crafting technique that's based on saliency maps.
Okay.
And this technique, it basically identifies the most influential pixels for a given classification.
Okay, so they're finding like the pixels that matter the most for the network's decision.
Exactly. And then by carefully perturbing those pixels, they can create adversarial samples that are very close to the original image.
Ah, so they're making it really hard to even detect that the image has been changed.
Right. The changes are super subtle. So this is a very challenging type of attack to defend against, which makes it a good test for their defense mechanism.
Makes sense. So they've got their data sets, their DNN architectures, their adversarial crafting method, and they've trained models both with and without defensive distillation. So now they're ready to see how it all performs in practice.
Yeah, this is where it gets really interesting.
Right, this is the moment of truth. How effective is this defense against these carefully crafted adversarial attacks? What did the results show?
Well, the results are pretty remarkable, actually.
And that's where we'll pick things up in part 2 of this deep dive.
For MNIST, defensive distillation, it reduced the success rate of adversarial sample crafting from 95.89% to just 1.34%.
Wow, that's a huge reduction. So basically, for MNIST, the defense mechanism almost completely neutralized those adversarial samples. That's incredible. What about CFAR10? Was it as effective on that data set?
For CFAR10, the results were still really impressive, although not quite as dramatic. Defensive distillation reduced the success rate there from 89.9% to 16.76%.
Okay, so still a significant improvement, though. Bringing it down from, almost 90% to under 17% is nothing to sneeze at. It definitely seems like defensive distillation makes these DNNs much more resilient to these kinds of attacks.
Yeah, for sure. And, we talked earlier about how they investigated the impact of the distillation temperature.
Right. What do they find there?
Well, their experiments showed that as you increase the temperature, generally adversarial sample crafting gets more and more difficult.
So it's like the higher the temperature, the more we're blurring the DNN's vision, so to speak, making it harder for those attackers to find those exploitable features, right?
Exactly. But, they also found that there's a kind of elbow point where after a certain temperature, increasing it further doesn't really give you much more benefit in terms of robustness.
Okay, so there's like a sweet spot
Mm-hmm.
where you're getting the maximum robustness without sacrificing too much accuracy.
Right. It seems like there's a limit to how much you can blur that DNN's vision before it starts to hurt its ability to classify things correctly.
Makes sense. Now, a crucial question is, how did defensive distillation affect the overall accuracy of the models? Because we don't want to gain robustness at the cost of losing accuracy, right?
Yeah, absolutely. And the good news is they found that for both data sets, defensive distillation didn't really hurt the classification accuracy very much at all. For MNIST, the accuracy dropped by less than 1.28% across all temperatures, and for CFAR-10, the biggest decrease they saw was only 1.37%.
Okay, so a very small price to pay for a big gain in security. Now, the paper also goes into a pretty detailed analysis of how defensive distillation affects the DNN sensitivity to those input variations. They look at the distribution of adversarial gradient amplitudes. Can you explain what that is exactly?
Yeah, so those adversarial gradient amplitudes, they basically measure how much the network's output changes when you make these tiny, tiny tweaks to the input.
Okay, so it's a way of quantifying how sensitive the network is to those adversarial perturbations.
Right. And their analysis showed that distillation, especially at those higher temperatures, it significantly reduces the average absolute value of those gradients. Like, in some cases, they saw a reduction by a factor of, get this, 10 to the power of 30.
Wow, 10 to the power of 30. That's an insane reduction.
Yeah.
So it's not just making the network less sensitive, it's practically flattening its sensitivity to those adversarial tweaks. That must have a huge impact on the network's robustness, right?
Definitely. And that's exactly what they found when they calculated the robustness, which, remember, is the average minimum perturbation you need to create an adversarial sample. For MNIST, they saw the robustness go up by like 790%. And for CIFAR-10, they saw a 556% increase.
Okay, so those are really significant improvements. This seems like pretty strong evidence that defensive distillation really does make DNNs much more robust, less susceptible to those adversarial manipulations. And it also seems to support the idea that it enhances their generalization capabilities, which we talked about earlier.
Yeah, it's like teaching the DNN to see the forest for the trees, instead of getting hung up on those tiny details that the attackers are trying to exploit.
I like that analogy. Now, did they look at any other effects of defensive distillation besides robustness and sensitivity? Like, for example, did they see any impact on the DNN's confidence in its predictions?
Yeah, they did touch on that a little bit. And what they found is that as you increase the temperature, the average confidence on the CIFAR-10 dataset actually goes up.
Interesting. So it seems like the network is not only becoming more secure, but also more confident in its decisions.
Exactly. But it's important to note that while defensive distillation looks really promising, there are some limitations, and the paper does acknowledge those.
Okay, so what are some of those limitations?
Well, one limitation is that right now, defensive distillation is only really applicable to DNNs that produce an energy-based probability distribution.
Okay.
So it might not be directly transferable to other types of machine learning models without some significant changes.
So this is a big step forward, but there's still work to do to expand its applicability to a wider range of models. Makes sense. Any other limitations?
Yeah, another thing is that the evaluation in this paper, it focused on a very specific type of adversarial attack, and it used a particular distance metric to quantify those perturbations.
Okay.
So more research is needed to see how defensive distillation performs against other attack methods and with different ways of measuring those perturbations.
That's a good point. We need to make sure it's robust against a wide range of threats, not just this one specific type of attack. Now, one question that comes to mind is, could defensive distillation actually start an arms race between attackers and defenders? Like, could attackers develop new techniques specifically designed to target models trained with defensive distillation?
That's a good question. But the authors argue that defensive distillation doesn't really introduce new vulnerabilities for attackers to exploit. You know, those existing adversarial crafting techniques, they're already designed to be effective against a variety of models, regardless of whether they've been trained with distillation or not.
So it's more like it's raising the bar for attackers, making their job harder, but it's not fundamentally changing the game.
Right.
Okay, so defensive distillation seems to be a very promising approach to defending DNNs against these adversarial attacks. It improves robustness without sacrificing accuracy, and it doesn't seem to introduce new vulnerabilities. But as with any new technique, there's still more work to be done, more research to be conducted. The paper outlines some interesting directions for future research. What are some of those?
Well, one thing they highlight is the need to investigate how well defensive distillation works with other DNN models and architectures beyond the ones they tested in this paper.
Okay, so basically seeing how widely applicable this technique is across different types of neural networks.
Exactly.
What else?
Another interesting direction is to see if defensive distillation can be adapted to other machine learning tasks beyond just classification.
Okay, so like applying it to regression problems or clustering or reinforcement learning.
Exactly. And finally, they emphasize the need for more research on developing and evaluating different definitions of robustness.
So going beyond the specific metric they used in this paper and looking at other ways to quantify and measure robustness.
Right. Because robustness is a complex concept, and there are probably many different ways to think about it and measure it.
Makes sense. So to kind of wrap up this deep dive, we've learned about a really important issue in deep learning security, explored a pretty powerful new defense mechanism, and identified some exciting avenues for future research.
Yeah, it's been a really fascinating look into the world of adversarial machine learning.
Before we go, I'd like to leave our listeners with a bit of a thought-provoking question, building on what we've discussed today. So the paper primarily focuses on defending against these adversarial attacks in the context of classification tasks, right?
Right.
But there's a whole world of other machine learning tasks out there. Regression, clustering, reinforcement learning, all sorts of things. Each of those tasks has its own unique challenges and vulnerabilities when it comes to these adversarial attacks.
For sure.
So the question is, how can we adapt and extend these principles of defensive distillation to protect those other types of machine learning models and systems from being manipulated?
That's a great question. And it's one that I think is going to drive a lot of exciting research in the years to come. Imagine a world where our machine learning systems are not only accurate and efficient, but also inherently secure and trustworthy no matter what task they're performing.
That's a vision worth striving for. And with his groundbreaking work on defensive distillation, we're one step closer to making that vision a reality. Thanks for joining us on this journey of exploration and discovery.
It's been a pleasure diving deep into this important topic with you and our listeners.
So it sounds like we're left on a bit of a cliffhanger. What were those remarkable results you mentioned?
Oh, right. So with defensive distillation, the success rate of those adversarial attacks on MNRIST plummeted from 95.89% to a mere 1.34%. Basically, it almost completely shut them down.
That's incredible. Almost a 99% reduction in effectiveness.
Yeah.
What about CFAR-10? Was it as dramatic?
For CFAR-10, the results were still really good, though not quite as drastic. The success rate dropped from 89.9% down to 16.76%. Still a huge improvement, though.
Absolutely. I mean, going from nearly a 90% success rate to under 17% is massive. It really highlights how much more robust the DNN becomes with defensive distillation. But remember how we talked about the distillation temperature and how it might play a role?
Yeah.
What did they find when they experimented with different temperatures?
Well, they found that as the temperature increases, cracking successful adversarial samples gets increasingly harder.
It's like we're intentionally blurring the DNN's perception, making it harder for the attacker to pinpoint those features to exploit, right?
Exactly. But here's the catch. They also found that after a certain point, cranking up the temperature even further doesn't really provide much additional benefit in terms of robustness.
Makes sense. You can only blur things so much before it starts to affect the network's ability to classify correctly. Did they find that sweet spot?
They did. They called it the elbow point, where you're getting the maximum robustness without sacrificing accuracy.
Okay, so that addresses robustness, but what about the overall accuracy of the models themselves? Did defensive distillation negatively impact their performance?
Not significantly at all. For MNIST, the accuracy actually only dropped by less than 1.28% across all the different temperatures. And for CFAR-10, the biggest drop they saw was just 1.37%.
It's a tiny price to pay for a huge increase in security. It seems like a worthwhile trade-off. The paper also did a deep dive into how sensitive the DNN becomes to those tiny input tweaks with defensive distillation. They analyzed the distribution of those adversarial gradient amplitudes, right?
Right. You see, those adversarial gradient amplitudes measure how much the network's output changes when you make tiny, tiny tweaks to the input. Essentially, it tells you how sensitive the network is to those adversarial perturbations.
Okay, so it's a way to quantify how much those adversarial tweaks are actually affecting the network's decisions. So what did they find when they looked at these with defensive distillation?
Their findings show that distillation, particularly at higher temperatures, dramatically reduces those gradient amplitudes, like sometimes even reducing them by a factor of 10 to the power of 30. Can you believe that?
10 to the power of 30.
Yeah.
That's a mind-boggling reduction. We're not just talking about making it less sensitive. We're practically talking about making the network completely ignore those adversarial tweaks. That must have a huge impact on robustness.
And it does. When they calculated the robustness, which, remember, measures the average minimum change needed to create a successful adversarial sample, they saw huge increases with defensive distillation. For MNIST, the robustness jumped by a whopping 790%. And for CFAR-10, it still saw a massive 556% increase.
Wow, those are some serious gains in robustness. It really highlights the effectiveness of this technique. It makes the network less susceptible to those small targeted manipulations. Did they explore any other effects of defensive distillation beyond robustness and sensitivity?
They did briefly look into the impact of distillation on the DNN's confidence in its predictions.
Oh, interesting. What did they find there?
Well, they observed that as the temperature goes up, the average confidence on the CFR10 dataset also increases.
So not only is the network becoming more secure, but it's also becoming more sure of itself.
Exactly. It's like it's gaining this inner confidence along with that robustness.
That's fascinating. Now, we've talked a lot about the positives of defensive distillation, but were there any downsides or limitations mentioned in the paper?
Yes, the authors do acknowledge some limitations. One key thing is that, as it stands now, defensive distillation only really works for DNNs that have a specific kind of probability distribution, what they call an energy-based one.
Okay, so that means it might not work right out of the box for other types of machine learning models. We might need to adapt the technique.
Exactly. Another point is that their evaluation focused on a particular kind of adversarial attack, using one specific way to measure those perturbations. Future research needs to investigate how well defensive distillation holds up against other types of attacks, using different measurement methods.
That makes sense. The world of adversarial attacks is constantly evolving, so we need to ensure this defense is robust against a wide range of threats. Now, another question that comes to mind. Could defensive distillation inadvertently start an arms race between attackers and defenders? Could attackers develop new strategies specifically to bypass this defense?
That's a valid concern. However, the authors argue that defensive distillation doesn't really create any brand new vulnerabilities for attackers to exploit. The existing attack techniques are already designed to work against a variety of models, regardless of whether they've been distilled or not.
So it's more about raising the bar for attackers, making their job harder, rather than creating a whole new set of vulnerabilities they can target.
Exactly.
It's great to see this progress being made in defending against these adversarial attacks. But like with any new technique, we need to continue researching and exploring. What directions for future research did the authors suggest?
One thing they highlighted is testing defensive distillation with other types of DNNs beyond the ones they used in this paper. Basically seeing how widely applicable this technique really is.
So expanding the scope to different neural network architectures. Makes sense. What else?
They also suggested looking into whether defensive distillation can be applied to other machine learning tasks beyond classification, like regression, clustering, or even reinforcement learning.
So adapting and expanding this concept to tackle different types of problems. That's exciting. Any other areas for future exploration?
Yes, they stressed the need to develop more ways to define and measure robustness, going beyond the specific metric they used in this paper. You see, robustness is multifaceted, and we need a deeper understanding of its various dimensions to build truly resilient systems.
That's a crucial point. This paper gives us a solid foundation to build on, but there's always more to explore, more to discover, and more to learn. And on that note, we come to the end of our deep dive into distillation as a defense to adversarial perturbations against deep neural networks. We've learned about a critical issue in machine learning security, explored a powerful new defense mechanism, and uncovered a wealth of exciting avenues for future research. Thanks for joining us on this journey, and until next time, keep exploring, keep questioning, and keep diving deep.
It's been a pleasure, and keep those brains buzzing.